Namaskar. The clock has struck 9 and welcome to this third episode of Know the Nobels Forum 2023, whereby we are bringing to you the Nobel laureates who are being announced every passing day. We all know that in the first week of October, the Nobel Foundation in Sweden, they announced the Nobel laureates across medicine, physics, chemistry, literature, peace, and economic sciences on consecutive days. And today is the day 3 of the Nobel announcement. And today, yet another triumvirate in the field of chemistry. They have been bestowed upon the prestigious Nobel Prize in Chemistry for the year 2023. So, and you can see that a lot of colors are in the air. Chemistry is all about color. Like those who are deeply into it, it's the optical sense what we all get from the phenomena of physics of light. It has a deeper chemical component as well. And these Nobel laureates have been recognized the highest honor, which has a legacy of around 120 odd years for adding color to nanotechnology. So as you can see that I am donning quite a colorful t-shirt out here just to commemorate, just to celebrate the phenomenon of colors which these Nobel laureates have brought in. So let's resume our deep dive into what is the lovely story. In fact, it's Nobel stories are nothing less than a Bollywood flick. इसमें बहुत सारे twists and turns हैं, बहुत सारे romantic sagas हैं, because Nobel Prizes don't come easily. These laureates would have put up an entire lifetime of theirs to the pursuit of their academic excellence. And as you might, we would encourage you to go to the Nobel Prize website, whereby their first reaction, somebody is in a class at a very advanced age, born in 1943, born in 1945, so on and so forth. And the lifelong pursuit, जीवन भर का जो तपस है, towards a very, very specific goal of theirs with huge perseverance. I think that is the celebration. That is the Nobel spirit which all these laureates come along with the highest scientific accomplishment. And they are the living legends of our times. We are not reading about them in textbooks in the bygone era. They are the living ones. And when the Nobel week will commence in the first week of December, all these Nobel laureates would be flying down to Stockholm, and they would be giving their Nobel lectures on the phenomena of what they have discovered, their lifelong pursuit over there. And as Alfred Nobel in his will mandated that these Nobel Prizes have to go to those people who have the greatest benefit to humankind, the prize money is not that very, very substantive considering the kind of moolah which the technocrats, the unicorns of the day, which the exploiters of these scientific discoveries actually make in the commercial world. As we discussed even yesterday, that it is the prize money total for one category of awards is 11 million Swedish kronas, which translates to around 1 Swedish krona is 7.49 Indian rupees. So around 7.5, 7.7 crore Indian rupees is the quantum. So if there are 3 laureates, so you can see that 2.5 crore ke lagbhag 2.5 crores is the kind of prize money which goes to for a lifelong pursuit. So it's not just about the prize money, it is the prestige, it is the highest accomplishment in the scientific space. And so today it will be converging after medicine, physics, and chemistry, the science part of it all. So let's unravel the story. आज के इन 3 नोबेल लॉरिएट्स की जो कहानी है, जो किस्सा है, और जो फिनोमिना, जो कलरफुल फिनोमिना, they have added color to nanotechnology. The Nobel citation, it reads that the Nobel Prize in Chemistry 2023 has been awarded to Maungi Bawendi, Louis Bruce, and Alexei Akimov, and for the discovery and synthesis of quantum dots. So is bar, as we have seen in the last 2 episodes as well, that microcosmos has become the focus of the Nobel Committee this year. Yesterday we saw that seconds, the discovery of synthesizing pulses of the range of seconds was the focus of the Nobel phenomena, the physics phenomena for the year. So similarly, today, chemistry has come up with the phenomena of quantum dots. So independently of each other, these three, Trimurti jisko hamare kehte hain. So as we can see that singular Nobel prizes are lesser given, minimum 2 or 3 singular prizes, maybe in literature or peace or some other phenomena. But scientific discoveries have become quite interdisciplinary. They have got quite intertwined, and even stages and layers of discovery. One of the laureates create a kind of a theoretical foundation, the other makes a practical and applied aspect of it all. So this interdisciplinarity is coming out, the convergence is coming out in a phenomenal way. What the 4th industrial revolution is being talked about. So independent of each other, Akimov and Bruce succeeded in creating quantum dots. So these 2 gentlemen, they somewhere created the theoretical foundations, the experimental part of it all. And Bawendi, he revolutionized the chemical production of it all. So yesterday we saw that also that production of nanoseconds, the experimental part, production was done by 2 scientists. The theoretical foundation was done by 1 lady a decade back, and that's how the scientific pursuits keep on going. So quantum dots now illuminate computer monitors and television screens based on the QLED technology. So the most expensive television sets which we might be going to buy, which we have probably bought during these festive occasions, belonging to the QLED technology, quantum dots use it. So the commercial application has been there in vogue for a long time, but then the Nobel Committee chose it this year for its own reasons, out of all the nominations which come to them. And so quantum dots also add nuance to the light of some LED lamps, and biochemists and doctors use them to map the biological tissue. So invariably, every scientific discovery, apart from the leisure and fun and the jazz applications of it all, invariably there is a medical application behind all these scientific discoveries. And we have with us Dr. Surbhi Vash Mittal, medico par excellence from the prestigious All Indian Institute of Medical Sciences. So she would be joining in, telling that how like the attosecond physics, what was discovered, it has a medical diagnostics impact. The mRNA nucleoside based vaccines, that was a medical splendor in its own might. And even today when quantum dots are being talked about, so the medical application, mapping the biological tissues, because human body again remains one of the finest manifestations of the cosmic creation, which scientists across the human mind has been trying to unravel. So it's a longer presentation today. The phenomena is quite intense. We will rush through a bit, but then this introduction was important to celebrate this spirit of colors, the colorful chemistry, as we all get to know all about it. So Maungi G. Bawendi, Louis C. Bruce, and Alexei Akimov are awarded the Nobel Prize in Chemistry 2023 for the discovery and development of quantum dots. So these are the illustrations from the Nobel website. So see the kind of colors they have tried to bring in into the whole supposedly, I would say, unassuming the word of chemistry. People find, the youngsters find a bit intense, but then when we see its applications all around, it really enthuses us to really go deeper into it. So quantum dots, these are tiny particles. They have unique properties and now spread their light from television screens and LED lamps. They catalyze chemical reactions, and their clear light can illuminate tumor tissue for a surgeon. So huge life-saving application these quantum dots have. So ye hain kya? Let's try to understand. So I would like Dr. Surbhi to introduce this slide to you all. It starts with a kind of technicolor word. Nobel Committee is also trying to bring in, I really encourage, this is all from the press release from the Nobel Committee. We have tried to give it a kind of a presentation outlook that Nobel, these papers, the scientific background paper, what they put up with every prize, it has, in very layman terms, it explains it also. A very complex scientific phenomena. The top scientists of the world, they really present it in such a lucid and incomprehensible fashion. So over to Dr. Surbhi.
Tutu, I have a feeling we are not in Kansas anymore. Is a classic quote from the film The Wizard of Oz. 12-year-old Dorothy faints onto her bed when her house is swept away by a powerful tornado. But when the house lands again and she steps outside the door, her dog Toto in her arms, everything has changed. Suddenly, she is in a magical technicolor world. If an enchanted tornado were to sweep into our lives and shrink everything to nano dimensions, we would almost certainly be as astonished as Dorothy in the land of Oz. Our surroundings would be dazzlingly colorful and everything would change. Our gold earrings would suddenly glimmer in blue, while the gold ring on your finger would shine a ruby red. If we tried to fry something on the gas hob, the frying pan might melt, and our white walls, whose paint contained titanium dioxide, would start generating lots of reactive oxygen species.
So friends, this is a lot of topsy-turvy technicolor word, which will be understanding that how the size at the nano word level, how the colors manifest, and how the Doppler effect, which we study in the physics, somewhere at the nano level, how the particles start behaving differently. So this is the whole mystery of the discovery what these Nobel laureates have brought about. So yeah, Dr. Surbhi, you can take it.
In the nano world, things really do behave differently. Once the size of matter starts to be measured in the millions of a millimeter, strange phenomena start to occur. Quantum effects that challenge our intuition. The 2023 Nobel laureates in chemistry have all been pioneers in the exploration of the nano world. In the early 1980s, Louis, Bruce, and Alexei Kumov succeeded in creating independently of each other quantum dots, which are nanoparticles so tiny that quantum effects determine their characteristics. In 1993, Mongi Bawendi revolutionized the methods for manufacturing quantum dots, making their quality extremely high, a vital prerequisite for their use in today's nanotechnology.
So two aspects I would like to emphasize upon on this slide, that yesterday when we looked at the attosecond physics, it was attosecond is 1,000th of a femtosecond. So the very small dimension matter starts behaving. The whole purpose of physicists has been to see the dance of electrons at the subatomic level. We saw that how infrared laser beam affected the movement of an electron, and how the low pulses were released out here. And today, from the dimension of time, it comes to the dimension of space. So nano is 10 to power minus 9. Atto, we saw that it was 10 to power minus 18. So how the dimensions, at the smaller dimensions, physics is being played. Yesterday we saw at the center it was a heart, and on the right side it was all about the life of the universe in seconds. So, and on the left it was in attoseconds. So then the comparison was made that a heartbeat is around 1 second. So 1 second is to the life of the universe, which is 13.6 billion years. Those many seconds, those many attoseconds are there in 1 second. So similarly, this is the size of a football, which we all are quite conversant with. And this football simile has been there across our physics and chemistry classes, whereby we've been studying atomic models from J.J. Thomson to now very, very complex and very, very refined models of quantum physics. On the right, it is the size of the Earth. So a quantum dot is a crystal that often consists of just a few thousand atoms. In terms of size, it has the same relationship to a football as a football has to the size of the Earth. So we can see that this is the kind of, I would say, two extremities at the macro level and at the micro level. Today being the space week, starting of the space week, 4th of October to 10th of October, the whole 7 days are commemorated as the space week. So in space, we talk about light years, the distances are measured over there. So, and this is the microcosm, whereby a quantum dot, which is a crystal, and this is the backdrop of all the modern technology, what we are unleashing out here. So one of the main purposes behind Know the Nobels Forum is to really make the youngsters excited about the scientific phenomena which is there in our day-to-day lives, and to get in awe and reverence about the charms of the cosmos which exist all around us. Not to get lost in the complexity, but to really fall in love with that, to really be in tandem, be in resonance with the cosmos and find a purpose. So these forums also have a philosophical purpose, because all these scientists, all these Nobel laureates, they have just put up, khapaufied their entire life to come to this level of excellence. When people are knowing we are not even able to pronounce their names properly, they are not the cine stars or the sports personality or the political order, but they are the real movers and shakers of humankind, giving humankind terrific power, which each one of us are privy to. We are utilizing it in our daily lives. So we should really be thankful and grateful to this Rishi Pragya, what we call it in Indic pantheon. See that they have been creating knowledge, advanced experiments for the greatest benefit to mankind. So, so we have to really view it in this fashion. Maybe not all of us might be pursuing a career in deep research, advanced research, going for doctoral studies, postdoctoral ones, and then for decades and decades working on a phenomena. But at least our consciousness about the real heroes, the real titans, should be very, very much. So thanks to the work of the laureates, humanity is now able to utilize some of the peculiar properties of the nano world. Quantum dots are now found in commercial products and used across many scientific disciplines, from physics and chemistry to medicine. But we are getting ahead of ourselves. Let's uncover the background to the Nobel Prize in Chemistry 2023. So yesterday when we saw Nobel's, that the real researches were in 1980s, then 1990s, the experimental background happened. So this phenomena has quite being in vogue. The applications have been quite in vogue. But then Nobel committees take almost 2.5 to 3 decades to really acknowledge that contribution to the level of being a Nobel Prize winning one. So moving forward, so for decades, quantum phenomena in the nano world were just a prediction. When Alexei Ekimov and Louis Bruce, these are the two theoretical foundational people, produced the first quantum dots. Scientists already knew that they could, in theory, have unusual characteristics. So theoretical foundations were already there. And way back in 1937, the physicist Herbert Froelich had already predicted that nanoparticles would not behave like other particles. He explored the theoretical consequences of the famous Schrodinger equation, which shows that when particles become extremely small, there is less space for the material's electrons. And in turn, the electrons, which are both waves and particles, the dual nature, when electrons are squeezed together, Froelich realized that this would result in drastic changes to the material's property. So again, it all boils down to the enchanting electrons down at the atomic level. And since we saw football in the atomic structure in the most simplistic fashion, the nucleus is at the center like a football in a football field, and electrons are making all the fun and the game all across the football ground. So at the nano level, when electrons are squeezed together, they really produced some kind of anomalous or a very exciting property. So anomalous is not in the negative connotation, but it can be very attractive and giving things out there. So you can see that it took so much of time because science advances, technology advances, a lot of things start happening. So researchers were fascinated by this insight, this theoretical insight, and using the mathematical tools, they succeeded in predicting numerous size-dependent quantum effects. They also worked to try to demonstrate them in reality, but this was easier said than done because they needed to sculpt a structure that was about 1,000,000 times smaller than a pinhead. So working at such subatomic levels, such smaller levels, theoretically you can predict, but then practically to really make it happen, it was a tough task. But this these breakthroughs were done by the scientists Alexei Ekimov and Louis Bruce, who produced the first quantum dots experimentally. So I would request Dr. Surbhi to take on this slide. Yeah.
So few people thought quantum effects could be utilized. Still, in the 1970s, researchers did succeed in making such a nanostructure. Using the type of molecular beam, they created a nano-thin layer of coating material on top of a bulk material. Once the assembly was complete, they were able to show that the coating's optical properties varied depending on how thin it was, an observation that matched the predictions of quantum mechanics. This was a major breakthrough. But the experiment required very advanced technology. Researchers needed both an ultra-high vacuum and temperatures close to absolute zero. So few people expected that quantum mechanical phenomena would be put to practical use. However, now and again, science offers up the unexpected, and this time the turning point was due to studies of an ancient invention, colored glass.
So you can see that there is a continuity in science that across ages, across phases of science development. So this nanoparticle development was all from the studies of colored glass. Let's see how that study of this ancient science helped the creation of quantum dots. So this is quite very interesting. So one great point which was made was that a single substance can give glass different colors. Now this is quite strange, quite anomalous, which was first studied by Alexei. So the oldest archaeological finds of colored glass are from several thousand years ago. Glassmakers have tested their way to an understanding of how glass can be produced in all the colors of the rainbow, the Vibgyor. You can use various chemical substances and produce glass across colors. They added substances such as silver, gold, and cadmium, and then played with different temperatures to produce beautiful shades of glass. तो ये विश्वकर्मा जो ग्लास के रहे, उन लोगों ने ग्लास अलग अलग नाना प्रकार से, we know glass bangles of Firozabad. It's very refined industry. We keep on seeing how in various lovely shades the glasses molded, the shapes and the shades of glasses we all are very, very conversant with. So in the 19th and the 20th centuries, when physicists started to investigate the optical properties of light, the glass makers' knowledge was put to use. Physicists could use colored glass to filter out selected wavelengths of light. We all know, yesterday we saw that how the red light was mentioned to cycle so many billions of times. So physicists had their own way, the entire spectrum, Vibgyor. So this was the material part of it all, but physicists study it from a wavelength perspective, the colors of the various lights and the frequency associated over there. So they started using colored glass to filter out selected wavelengths of light for their experimentations. Now, in order to optimize their experimentations, they started to produce glass themselves. Now, this was the very interesting part. So physicists started becoming chemists in a way, and chemists in turn went to the physical phenomena. So at the very elemental level, it is all science converging in one. That is the convergence we can see all here. So it led to very, very important insights. One thing they learned was that a single substance could result in completely different color glass. For example, a mixture of cadmium selenide and cadmium sulfide could make glass turn either yellow or red. Now, this is non-determinism, which scientists were enchanted with. Which one it became dependent on how much the molten glass was heated and how it was cooled. So the material is the same, but then what color it will take, it dependent on two phenomena, that how much it was heated and how it was cooled. So they started observing this. Eventually, they were also able to show that the colors came from particles forming inside the glass and that the color dependent on the particles size. So this they could unravel in the 19th and 20th century earlier. So this was more or less the state of the knowledge at the end of 1970s. So very importantly, that the body of scientific knowledge, it moves collectively. So by 1970s, this was the state of our understanding, that why the same material is producing a glass of different colors. So if it can happen with glass, it can happen with other substances also. So when one of this year's laureates, Alexei Akimov, 1970s, a recent doctoral graduate, started working at the S.I. Vavilov State Optical Institute in what was then the Soviet Union. So this was Alexei Akimov, as we can see, it's a Russian name, a Russian scholar, a Russian scientist who started studying at the end of 1970s. So what was it all? So Alexei Akimov, he was born in 1945, just before the first atom bomb was to be delivered. So in the former USSR, he did his PhD in 1974 from Lvov Physical Technical Institute, St. Petersburg, Russia. And formerly, he was the chief scientist at Nanocrystals Technology Inc., New York, USA. So he moved on to USA at a later time. So what was his contribution? This picture we will come at a later part, but then there is a story of Alexei. The fact that a single substance could result in different colored glass interested Alexei Akimov, because it is actually illogical. If you paint a picture in cadmium red, it will always be cadmium red unless you mix in other pigments. So how could a single substance give glass of different colors? So this was the question onto which Alexei Akimov, a doctoral student, devoted himself to. So during his doctoral degree, Akimov studied semiconductors. So semiconductors are important components in microelectronics, And in this field of microelectronics, optical methods are used as diagnostic tools for assessing the quality of semiconducting material. Researchers shine light on the material and measure the absorbance of the light. This reveals what substances the material is made from and how well ordered the crystal structure is. So VLSI and all the chips we are talking about. So it all started from that discovery part. We'll come to this picture in a couple of slides. So Ekimov was familiar with these methods of semiconductor quality assessment of it all. So he began using them to examine colored glass. After some initial experiments, he decided to systematically produce glass that was tinted with copper chloride to a range of temperatures between 500 degrees Celsius to 700 degrees Celsius, varying the heating time from 1 hour to 96 hours. So this was the play he made to understand this phenomena that how the same material can produce different colors. So once the glass had cooled and hardened, he X-rayed it, used the very fundamental, the first line of diagnostics which doctors use even before going to the ultrasound or CAT scan, PET scan, and MRI and all. So he X-rayed this glass. The scattered rays showed that tiny crystals of copper chloride had formed inside the glass, and the manufacturing process affected the size of these particles. So the two variables what were there? How much it is heated and how long it is heated. So in some of the glass samples, they were only about 2 nanometers. In others, they were up to 30 nanometers. So copper chloride was tinted. So it came out in various sizes. So interestingly, it turned out that the glass light absorption was affected by the size of the particles, size of the copper chloride here. So the biggest particles absorb the light in the same way that copper chloride normally does. The biggest particles. But the smaller particles of 2 nanometers or so, the bluer the light that they absorb. As a physicist, Ekimov was well acquainted with the laws of quantum mechanics and quickly realized that he had observed a size-dependent quantum effect. Size-dependent quantum effect as demonstrated in the adjacent figure. Let's understand it a bit more by this lovely illustration. So quantum effects arise when particles shrink. So it's not called anomalous like the anomalous expansion of water we study in basic physics. So they say it's a quantum effect. Now the science has got refined. So these are the quantum effects. So when particles are just a few nanometers in diameter, the space available to electrons shrink. This affects the particles' optical property. Yesterday, we also saw that how the laser beam, pulsating laser beams, brought the electron out from the nuclear electrical field of the nucleus, and then they went out, and then had to return back to the same field. They shed off a small wavelength, the overtones over there, small wavelength, attosecond pulses out there. So size-dependent quantum effect, larger nanoparticle, more space for the electron wave. बड़ा है. Smaller nanoparticle, less space for the electron wave. So quantum dots absorb light. Quantum dots absorb light and then emit it at another wavelength. Its color depends on the size of the particle. So this is the kind of application. The larger the nanoparticle inside, so it will absorb the same, but smaller it becomes, it goes towards the blue curve. So this is the quantum dot phenomena. And in fact, we remember that producing the blue LED a couple of years back, the Nobel Prize was given to that very phenomena of championing the blue light. So this had something to do with this phenomena itself. So you can see that the Nobel Prizes across, they follow a kind of a continuum, and delving deep into these narratives is so very important. So this was the first time, Alexei Akimov, that someone had succeeded in deliberately producing quantum dots. So what was a quantum dot? When he heated the glass, which was tinted by copper chloride. So copper chloride crystals, glass samples, they were 2 nanometers or 30 nanometers. So quantum dots of copper chloride were created. So nanoparticles that cause size-dependent quantum effects. So this research was produced almost 40 years back in 1981. Akimov published his discovery in a Soviet scientific journal. But this was difficult for researchers on the other side of the Iron Curtain to exist. Now here comes your Nobel Prize in Peace, your humanities, that what was happening in 1981 at the geopolitical level. Cold War, the war between the two power blocks of United States of America and USSR was at its epitome. And both were fighting for prominence over there. So this research could not pass on. So therefore, this year's next Nobel Prize laureate in chemistry, Louis Bruce, was unaware of Alexei Akimov's discovery when in 1983, just 2 years after, he was the first researcher in the world to discover size-dependent quantum effects in particles floating freely in a solution. So I would like to give another instance that wireless, the discovery of wireless, as we all know, is recorded in our general knowledge books to Marconi. But then when you go deeper, J.C. Bose was the first to invent the wireless transmission of sound. So because India was under the colonial, I would say, subjugation, so here Cold War was the reason that Alexei Akimov's research could not reach to the US, because those times were not of the internet also. And these were all physical publications. So parallelly, scientific discoveries happen. So this year's Nobel Prize goes to Akimov and Bruce for independent discovery, independent creation of quantum dots. So his process was a bit different, but both of them came to the same conclusion. So Louis C. Bruce was born in 1943. He is an elder one, 2 years elder to Akimov. And he was born in Cleveland, Ohio, USA. And he did his PhD in 1969 from Columbia University, New York. And he's currently a professor at the Columbia University out there. The same university continues. So Louis Bruce was actually working at the Bell Laboratories in the US with the long-term aim of making chemical reactions happen using solar energy. So the purpose was solar energy. That's how penicillin was discovered. You are doing something deliberately, but then something else happened, and that's where your observation skills, why this is happening enormously, and then you devote yourself and a new discovery starts coming up. So to achieve this, he was using particles of cadmium sulfide, which can capture light and then utilize its energy to drive reactions. So the photovoltaic cells, what we are talking about. So this was cadmium sulfide in a solution. So they are trying at the chemical reaction level, kind of small energy storage, the chemical level batteries, you can say. And the particles were in a solution, and Bruce made them very small, particles of cadmium sulfide, because this gave him larger area on which the chemical reaction could take place. So now this comparison you would be studying in your chemistry classes also. Ki, more surface area comes when more particles, smaller shapes come, like the hills. In a smaller geographical stuff, they have much larger area because they are in a three-dimensional space. The surface area exponentiates phenomenally. So the more the material is chopped up, the greater the surface area. This is what they have explained. the greater the surface area, it will expose to its surroundings. So that was his purpose, to make small particles. He went to the 10 to power 9 minus 9 nano area. So during his work with these tiny particles, Bruce noticed something strange, that their optical properties changed after he had left them on the lab bench for a while. He guessed that this could be because the particles had grown. So to confirm his suspicions, he produced cadmium sulfide particles that were just about 4.5 nanometers in diameter. Bruce then compared the optical properties of these newly made particles with those of the larger particles, which had a diameter of around 12.5 nanometers. The larger particles absorb light at the same wavelength as cadmium sulfide generally does, but the smaller particles had an absorption that shifted towards blue. So this is the quantum effect which happens, that on one extreme, when the particle size becomes smaller, they don't show the phenomena of the larger crystal size. So just like Ekimov, Bruce understood that he had observed a size-dependent quantum effect, and he published his discovery in 1983, and then started investigating particles. So 40 years when his discovery was first published, 40 years he had to wait after his Nobel, when he could be accorded with the Nobel Prize winning. And then he started investigating particles made from a range of other substances. The pattern was the same. The smaller the particles, the bluer the light they absorb. So that is what this is the strange properties of particles and their quantum effect. So I would like to bring in Dr. Surbhi out here. Dr. Surbhi, what actually inspires these scientists to really stay put, keep working long hours, and for such a long duration? So how would you define this perseverance, where it all comes from?
And I think it's the research and scientific expeditions. These are primarily from the academic scintillation it provides. When you are doing an experiment and you reach a certain stage, you don't want to say quits. You want to delve deeper and further deeper. So because you've just reached, say, half the concept, and then the curiosity and the scientific temper, it motivates you to go to the very end and keep trying. One trial, hit and trial, or any experiment, it reaches you to a certain level. So, and there's so much of scientific learning, so much of benefit to mankind, so much of applications of so many discoveries, that it is a lifetime achievement kind of a thing.
You mean to say that in today's crass commercial world, when anyone is doing anything, the first question comes to the table, what is in it for me? We all talk about in the commercial parlance in terms of give and take. But I think the pursuit of knowledge is an end in itself. It's a sadhya in itself, and to which the pursuit of academic learning is what it drives these people. Because 40 years, who would have waited? I think Louis Bruce would not even have thought about it, that after his first publication, 40 years later, the same, I would say, phenomena would be awarded, and he would become a overnight luminary across, a Nobel laureate out there. So I think this is a great life message, a quantum leap we can have in our personal lives. And one of the very core reasons behind this Know the Nobels contest is to indoctrinate, is to impregnate these very Nobel qualities of the Nobel laureates, their perseverance, their dedication, their I would say their patience, and their enchantment. And I would really encourage, and had we the time, we would have played those scripts that, oh, I have a class at this point in time. They're so unusual. Even after being at the helm of the scientific discoveries, they're unassuming. So the humility of theirs makes them achieve this highest pedestal of human accomplishment ever. And perhaps most of us would never know about their names in the popular parlance, which is all, I would say, polluted or stridden with the cinema celebrities, the sports personalities, the political figures. The temporal phenomena takes care of our attention rather than these titans who really bring about the tempest in human knowledge. So moving forward, now this is very important for all the chemistry students. Periodic table, the holy grail of it all. So what this discovery has brought about, this scientific phenomena, now the periodic table is from a 2-dimension, it is going to becoming a 3-dimensional periodic table. So in a way, for all of us who have to study chemistry as a compulsory subject, it becomes tough. But then the excitement of it all is also so very phenomenal. So this is where you may be tempted to ask, why does it matter if a substance absorbance is slightly more towards blue? Iske implications kya hain? Why is that so amazing? Science is all about getting astonished. It is a wonder in itself. It's more than watching a Netflix, because if the awe and reverence, even in watching a phenomena, and today at the launch of the Space Week, we at Rethink India have given a list of 7 classical space movies on rethinkindia.substack.com, and the idea is, let's get enchanted with the phenomena of space through these popular motion pictures. So farak kya padna hai? Farak ki pehna? So well, the optical changes revealed that the substance's characteristics had completely changed. It is not just कि वो blue क्यों absorb कर रहा है. अगर उस छोटे level पे, उस nano particle पे 3.5 nanometers, 4.5 nanometers, its entire characteristics change, and which is at the physical level is expressed by its differentiated absorption, कि वो blue को absorb कर रहा है. A substance optical properties are governed by its electrons. This was the crude chemistry and physics we have been knowing. But the same electrons also govern the substance's other properties, such as its ability to catalyze chemical reactions or conduct electricity. So when researchers detected the changed absorption, they understood that in principle they were looking at an entirely new material. So again, this presumption, I want to bring it back the attention that this anomaly, the same material is producing यहाँ पे कि the same material, they are not the same material. They become different material because of their size. The material is same in terms of the other part, but their size is also one of the parameters. That is what it is saying. What Alexa started with कि भाई ये logical क्यों है? Because there was a hidden aspect that there was a size dependent quantum change which was happening. It's a third parameter which has come. So this is what is the third dimension of periodic table. So if you want to understand the magnitude of this discovery, उसको feel करना है. So you can imagine that the periodic table suddenly has gained a third dimension. And elements' properties are not only affected by the number of electron shells and how many electrons there are at the outer shell, but at the nano level, size also matters. A chemist who wanted to develop a new material thus had another factor to play with, of course, this tickled researchers' imagination. So there was just one problem with all this fundamental theoretical discovery. The methods Bruce had used to fabricate non-particles generally resulted in unpredictable quality. The quality was not up to the mark. Unpredictable quality. Quantum dots are tiny crystals, as we saw. What a quantum dot is to a football is to the size of the earth. So it's very easy to compare. And they are the ones that could be produced at that time, often containing very many defects. They were also of varying sizes. It was possible to control how the crystals were formed, so the particles had a given average size. But if researchers wanted all the particles in a solution to be about the same size, they had to sort them after they were made. And this was a difficult process that hindered development. So a scientific discovery, a principal discovery is one part, but in manufacturing it and then taking it to the commercial scale is yet another challenge. And that was championed by the third Nobel laureate, Maungi G. Bawendi, who was born in 1961, the youngest of the three, in Paris, France. So a Russian, an American, and a French. He did his PhD in 1988 from the University of Chicago, and he's currently a professor at the Massachusetts Institute of Technology, Cambridge, MA. So Maungi Bawendi revolutionizes the production of quantum dots. Like yesterday, we saw the two male physics laureates. They produced attosecond waves independently through their experimentations, through their laser beam stuff. So this was a problem that this year's third Nobel Prize laureate in chemistry decided to solve. So Maungi Bawendi started his postdoctoral training. So there is a continuity. His professor was Louis Bruce. So he started his postdoctoral training at Louis Bruce's laboratory in 1988, where intensive work. So Louis Bruce had done his, and then he set out his laboratory. So he was the researcher who made it happen. So where intensive work was underway to improve the methods used to produce quantum dots. So using a range of solvents, temperatures, and techniques, they experimented with a variety of substances to try and form well-organized nanocrystals. It's like when we are producing a recipe in the kitchen, how many iterations go into it. So scientific experimentation is more nuanced, more deeper out there. And the crystals were getting better, and they were still not good enough. So years and years of hard work. However, Bawendi did not give up. Like we saw in the case of the Madam Carlina using mRNA, stabilizing them, she did not give up. So this is one Nobel quality we are seeing across. They don't give up. When he started working as a research leader at the Massachusetts Institute of Technology, he moved on from Bruce Laboratory to Massachusetts, MIT. He continued his efforts to produce higher quality nanoparticles. So had he been here, the credit might have gone to Louis Bruce because he was the center head, but then he took that spirit and continued. And the major breakthrough came in 1993. So again, 1983, 1993. So these dates are also very, very seminal. And when the research group injected the substances that would form nanocrystals into a heated and carefully chosen solvent, they injected as much as of the substance as was necessary to precisely saturate the solution, which led to tiny crystal embryos beginning to form simultaneously, like the pakoras in a frying pan. It's a very well manicured aspect. You can see that if the same size pakoras have to be done, so the heating solution. So just imagine at the nano level, if it has to be produced, how cumbersome, how difficult it is all about. So one more thing which I would like to impress upon by way of these Know the Nobel forums is that applied sciences is so very important. We have stopped conducting experimentations, relishing our laboratory classes for want of theoretical understanding and cracking some of the other entrance examinations. But it is in the laboratory where you really develop a feel. The skill for solving a numerical is one part of the story. That's an intellectual pursuit. But then the art of science, it gets developed in the rasoi, in the laboratory, and one of the finest laboratories in all our households is our kitchen. Perhaps we can start doing something alongside the devouring of delicacies which are presented to us. So maybe I would like to bring in Dr. Surbi about her experimentation. Being a medico, medicos have to do a lot of hands-on training, learning, experimentation, and that's what make them employable from day one. So, Dr. Surbi, what do you have to comment upon on this part?
So, as I said, that it's a quest to excel and better your results, and it all brews from your constant drive to achieve a goal to find the solution. And so, be it a medical laboratory or a biochemist laboratory or even the kitchen, you're constantly trying to better the recipe, better the dish, get the results accurately, and as said earlier, the benefit mankind, the application part of it, that is humongous, because one discovery, one experiment which reaps such a beautiful result has mind-boggling applications, and in various sciences, in various sectors, in various fields, and that is a boon to mankind.
Lovely, lovely. So the applied part of science is so very intricate, and so this was the whole process. What Maungi Bawendi produced the quantum dots. This is the solvent. It's a schematic representation. This is the thermometer to measure the temperature. This is the stabilizing gas. So Bawendi injected substances that can form cadmium selenide into hot solvent. The volume was enough to saturate the solvent around the needle. So needle is a place where the crystals would start formulating. So small crystals of cadmium selenide immediately formed, but because the injection cooled and the injection cooled the solvent, the crystals stopped forming. So when Bawendi increased the temperature of the solvent, the crystals once again started to grow. So the longer this continued, the larger the crystals became. So he developed a process to change the size of the crystal. So this is more of an experimental laboratory driven, but this is the process he developed, that he kept on varying the temperature of the solvent. He created the crystals of varying sizes. So by dynamically varying the temperature of the solution, Maungi Bawendi and his research group succeeded in growing nanocrystals of a specific size. During this phase, the solvent helped give the crystals a smooth and even surface. So just see the kind of mapping which he had to do, like the tuning. What solvent? A very, very specific solvent. Now this becomes a kind of an industry secret if you go deeper into it. So what kind of solvent was used, what kind of a particle has to be created, and what temperatures it happens. So it's a whole continuum, a very empirical scientific process, what we all study. I would really encourage to really go to Maungi Bawendi's personal websites and go to his research papers. Most of it is available in the open domain. When it goes to the industrial corporations, that's a different matter. But academia is open because you have to solve a mystery of chemistry, mystery of the cosmos. So the nanocrystals that Bawendi produced were almost perfect. Yani ki same size ke pakode, the nanoparticles, giving rise to distinct quantum effects. Because the production method was easy to use, it was revolutionary. More and more chemists started working with nanotechnology. So 40 years back, nanotechnology came into vogue. 30 years back, it came into vogue. So we all know about 1993, 1991, all about the closing of the Cold War, or perhaps the opening of the global world, the globalization of it all. But then the nanotechnology took a major turn since 1993, when this application-based creation of nanoparticles started happening. So because the production and began to investigate the unique properties of quantum dots. So quantum dots are nothing but nanoparticles, and we have seen their implications out there. So the luminous properties of quantum dots have found commercial uses. So these quantum dots, the luminous property, there might be the chemical property, there might be other things, but luminous property, how it has found commercial uses, over to Dr. Surbhi, because at the end of the day, it has got a very strong medical utilization as well.
So 30 years later, quantum dots are now an important part of nanotechnology's toolbox and are found in commercial products. Researchers have primarily utilized quantum dots to create colored light. If quantum dots are illuminated with blue light, they absorb the light and emit a different color, modifying the size of the particles makes it possible to determine exactly what color they should glow. The luminous properties of quantum dots are utilized on computer and television screens based on QLED technology, where the Q stands for quantum dot. In these screens, blue light is generated using the energy efficient diodes that were recognized with the Nobel Prize in Physics 2014. Quantum dots are used to change the color of some of the blue light, transforming it into red or green. This makes it possible to produce the three primary colors of light needed in a television screen.
So as we can see that Nobel Prizes also have a continuum. So one Nobel Prize leading to another Nobel Prize. So we can see the entire history of science and technology. Technology comes after science has proven it out there. So moving forward, yeah.
Similarly, quantum dots are used in some LED lamps to adjust the cold light of the diodes. The light can then become as energizing as daylight or as calming as the warm glow from a dimmed bulb. The light from quantum dots can also be used in biochemistry and medicine. Biochemists attach quantum dots to biomolecules to map cells and organs. Doctors have begun investigating the potential use of quantum dots to track tumor tissue in the body. Chemists instead use the catalytic properties of quantum dots to drive chemical reactions. So as mentioned here, doctors and chemists are using the quantum dot mechanism, wherein we can use it to track tumor tissues in the body. So a very beautiful way of, you can see the CT scans, the PET CT scans, the detailed Tesla scanning. They're all using the QLED screens, the nanotechnology, because the more micro you go, the more accurately you are localizing the tumor in the body. So that's the application of it, perhaps.
So coming to the Nobel quest, the greatest benefit to the mankind. So quantum dots are thus bringing the greatest benefit to mankind. And we have just begun to explore their potential, like the way we have just begun to use the mRNA-based vaccines, the technology, the phenomena of changing the nucleoside bases and making the effect of mRNA vaccines. The way we have used attosecond physics, its impacts, understanding the phenomena of electrons, the applications would be quite varied. So we have just begun to explore the potential. QLED technology is one part of it all. We are all using these multiple light LED lamps without realizing that this is a Nobel Prize winning discovery, and how cumbersome from 1937 to 1980s, 83, 1993, and 2023, when this was formally recognized as a Nobel level phenomena. So researchers believe that in the future, quantum dots can contribute to flexible electronics, minuscule sensors, slimmer solar cells, and perhaps encrypted quantum communications. So rather than a diode or a VLSI level chip where the coding of 0 or 1, so within the size of it all, so quantum communications would also be possible. And one thing is certain, that there is a lot left to learn about amazing quantum phenomena. So if there is a 12-year-old Dorothy out there looking for adventure, the nano word has a great deal to offer. So thank you so much for this Know the Nobels Forum 2023, where we unraveled the mystery of the quantum dots, that how the periodic table has gone three-dimensional. The properties of a particle or has now another dimension of size associated with it, and how the stories of three Nobel laureates, two of them discovered the theoretical foundations of it all independently, just 2 years different aside, but because they were situated in two different parts of the globe, and then how geopolitics affected it. So, and then how the third Nobel laureate, who had a association with the second one, but he continued his pursuit. He did not give up. Had he given up, perhaps the mankind would have been bereft of the benefits what quantum dots are bringing to the fore. So with this, we conclude the Know the Nobels Forum 2023 on chemistry. And today, tomorrow, it will be 5th of October, and the Nobel Prize for Literature would be announced. And tomorrow is also the International Teachers' Day. And language is so very important, so very phenomenal. So literature, language, teaching, so it's all an intertwined word. We will be joining you again at 9 p.m. with the Know the Nobels Forum on Literature. And we hope that this elaborate session, deep dive, going double-clicking the Nobel phenomena, and also trying to create that what we have to learn from the laureates' lives per se, scientific phenomena apart, what is there for each one of us to learn is their stories of perseverance, persistence, endurance, and whatnot. So as Dr. Surbi said that, and in the Indian pantheon, we have always given knowledge as the highest value. ज्ञान प्राप्ति अपने आप में ही एक पुरुषार्थ माना गया है. So with this, I will request Dr. Surbi to say the concluding words, and we will close today's session. Yeah.
So thank you, viewers. We have unraveled the Nobel Prizes in chemistry today, and as said, they added color to nanotechnology, and this is the greatest benefit to humankind. Thank you.
So with this, namaskar.